The topic is electric potential. To determine electric field intensity, we used Coulomb's law and Gauss's law. The Coulomb's law is applicable for any charge distribution, while Gauss's law is applicable for any symmetric charge distribution. So these are the two laws through which we determine the electric field intensity. And here we study a new concept of electric potential to determine the electric field intensity E, because electric potential is a scalar quantity and it is better because it is easier to handle scalars than vectors. So here we study a new concept, that is electric scalar potential, which is represented by capital V. Now, as we know that the electric field intensity is force per unit charge, that is force upon cube. Q is the charge. So as we know, we consider an electric field. Electric field is originated from some positive charge. The source of electric field is positive charge and it terminates to negative charge, or if there is no negative charge, it terminates to infinity. So here we consider an electric field intensity or electric field. In this electric field we place a charge Q. The charge Q is at point A. Since this charge Q is positive charge, so it repels by the source of electric field Q. So it repels by that source and it moves in the direction of E. So here this charge having some force F, and that is equals to Q into E from this formula. Now this charge Q that is at a point A, and we wish to displace this charge Q from point A to some point B by some small differential length dl. Now this small differential length dl, and in terms of vector, dl vector makes some angle alpha with respect to force vector. While displacing from point A to B, there is some work done, and since this is a small displacement, so there is a small work done denoted by dw. Now dw is equals to F vector dot dl vector. The small differential work is equals to the dot product of force vector and dl vector. Now we know that F equals to Q into E. So here the dot product is changed to E dot dl. So apply a dot product E dot dl vector is equals to E dl cos alpha. Alpha is the angle between force vector and dl vector. So this is a small work done from point A to B. Now we focus on this angle alpha. When this angle alpha is greater than 0 degree and but less than 90 degree, then the work is done by the field. This means that when the angle alpha is less than 90 degree but greater than 0, the work is done by the field, means it is repelled by that source of electric field. So there is a work done that is by the field. Now when this angle alpha is greater than 90 degree but less than 180 degree, means we required a work done against this electric field. So we require some external source to do this work against the field. So this is called a negative work. So in this case, the cos alpha angle for second case is negative. Cos alpha is negative. So dW in this case is minus F dot dl. Here the minus sign means the work is done by the external source, or you can say that negative work is done by the field. In case 1, the positive work is done by the field. In second case, the negative work is done by the field, that is against the field. So dW is equals to minus F dot dl, and F dot dl force is equals to Q into E, so it is called minus QE into dl vector. So this is a small work done dW, and to determine the total work done from moving A to B, we use an integration. So we integrate it from point A to B. Q is constant, so we can write the equation 1, that is work done W is equals total work done W is equals to minus Q integration E dot dl. The limit is from A to B. A is the initial point and B is the final point. The potential energy is required in moving Q from A to B, means there is some potential energy which is required to move charge Q from point A to B against the field, that is negative work is done by the field. Now the term potential difference. Potential difference is denoted by capital V suffix AB. AB are the 2 points. Here A is the initial point and B is the final point. So from equation 1, the ratio work W upon Q is called a potential difference. Work done per unit charge is called a potential difference, and the formula is we take Q at the denominator side and the remaining part is minus integration E dot dl. So this is a formula of potential difference, and the unit is joule per coulomb. Joule is the unit of work and coulomb is the unit of charge, or simply the unit is volts. So these are the two equations, equation 1 and equation 2. Or the potential difference in a simple way can be written as VAB is equals to VB minus VA, where VA and VB called the absolute potential at point A and B respectively. Both VA and VB have same zero reference point, that is origin, means at a point A the potential is VA and at point B the potential is VB. These potentials are called absolute potential, means with respect to origin. Means with respect to origin we can determine the absolute potential, but with respect to 2 points we determine the potential difference VAB. So there are some points to be noted. First is to determine VAB, that is the potential difference, A is the initial point while B is the final point. And second point is when potential difference is negative. Negative means VB is less than VA, or VA is greater than VB. Then only we get a negative potential. Means there is a loss of potential energy is moving charge Q from A to B. That is, work is done by the field. When potential difference is negative, the work is done by the field. And when potential difference is positive, means gain in potential energy. In this case, VB is greater than VA. The final point potential is greater than initial point potential. Then there is a gain in potential energy. That is, this is a case of an external agent performs the work, that is against the electric field. The next topic is the potential field of a point charge capital Q. Here we consider a point charge Q situated at the origin. Since this charge is positive, then the electric field is originated from this point charge and terminated to the infinity in all the direction. So here we consider an electric field due to point charge. Now in this field we take two points, point A and point B. The point A having a position vector RA, while the point B having a position vector RB. Now our task is to determine the potential from moving from point A to point B. Now the path is any way. It may be of any shape. So we consider here a path from A to B point, and on this path we assume a differential length dl, and this dl having a position vector r or a distance small r. Means the dl, the differential length, is at a distance of r with respect to origin, because charge Q is located at the origin. And we know that the electric field due to a point charge is given as equation 1, that is E equals to Q upon 4 pi epsilon naught r square in the direction of r. And also we know that the potential difference VAB is equals to minus integration E dot dl, the limits from A to B. Since here a point charge Q is spherical in shape and the electric field is originated from this positive charge in all the three directions, means it acquires a spherical shape. So here we consider a spherical coordinate system. Now in spherical coordinate, so this is a differential length. So the dot product of equation 1 and differential vector dl is only r component, because the dot product of unit vector r and unit vector r is 1, while the dot product of unit vector r dot unit vector theta and unit vector r dot unit vector phi is 0, because the angle between them are 90 degree. So we get only the r component, that is unit vector r. So after the dot product we get only dr. So we have to integrate with respect to r. Now here we take minus sign, and the limit is from RA to RB. RA is the position vector of point A and RB is the position vector of point B. That is initial to final. Now, after calculating this integration, we get a potential difference, that is Q upon 4 pi epsilon naught within bracket 1 upon RB minus 1 upon RA. So this is the potential difference due to a point charge Q while moving from point A to point B. Or as we know that potential difference VAB is equals to VB minus VA. So this is a convention. VB minus VA means B minus A, that is position vector 1 upon RB minus 1 upon RA. Now let us assume an infinity as reference. Till now we assume that reference point is origin. Now we assume that infinity as reference, and at the infinity the potential is 0. So we take a point A as a reference point. So at point A the potential is 0. So VA equals to 0, and this position distance RA is infinity. The point A is at infinity, so this distance tends to infinity. So after putting the value of RA is equals to infinity, the 1 upon infinity is equals to 0, so we get only 1 upon RB. And the potential at any point, so in general the potential at any point, that is RB equals to R, we take a general point due to a point charge located at origin is V equals to Q upon 4 pi epsilon naught R. So this is a general formula to determine the potential due to the point charge Q located at the origin. And here the origin point, the initial point is infinity, and final point is some point, some any point. So in terms of integration, the potential is equals to minus E dot dl, and the limit is infinity to some point R. So from this equation we observe that the potential at a distance R from the point charge is the work done per unit charge by an external agent in transferring a test charge from infinity to that point. Means here the work done is against the electric field. So the work done is by the external agent, and the work is done from moving a charge Q from infinity to some point R. So potential at a distance R is minus integration infinity to R E dot dl. Now the relationship between E electric field and potential V, and here we get Maxwell's equation. So to get this relationship we consider a 2 point A and a neighboring point B. And here we take a Cartesian coordinate system. So the point A has coordinate xyz and the neighboring point B has coordinate x plus dx, y plus dy and z plus dz. Means we displace from point A to point B by some small distance. So there is a differential increase in potential also, and this is written as dV. By using calculus, dV is equals to del V upon del x dx plus del V upon del y dy plus del V upon del Z dz. So here this is from our mathematics, that is from calculus. dV can be written in this form, having three variables. So this dV can be written in terms of unit vectors. So this is a dot product of these two vectors, that is this can be a del V upon del x unit vector x plus del V upon del y unit vector y plus del V upon del z unit vector z dot dx unit vector x plus dy unit vector y plus dz unit vector z. Means when you calculate the dot product of these two, we get the dV in this form. So this first is called a gradient of a potential. So from first unit we know that this is called a gradient of a potential, means gradient of a scalar. The gradient is operation that is performed on a scalar quantity, and this second one is a formula of differential length in Cartesian coordinate system. So from here dV is equals to del V dot dl. Okay, so gradient of a scalar, the gradient of a scalar results a vector, and the dot product of two vectors gives a scalar one, that is dV. dV is a scalar one. So here del V, gradient of V is dV upon dl. So first equation is dV and second equation is in terms of gradient del V. So since potential V is equals to minus integration E dot dl, okay, so the differential increase in V, that is dV. So in terms of dV we get an approximate value of this one. Integration is replaced by an approximation. So dV is equals to minus E dot dl. So this is the third equation. So from equation third and equation number 2 we get del V is equals to minus E dot dl upon dl. So dl is cancelled and we get only minus E. So we can write E equals to minus gradient of V. So we can calculate the electric field intensity from potential. The electric field intensity is gradient of a potential. The negative sign shows that the direction of E is opposite to the direction in which potential increases. So the potential, that is a new concept